Okay, exercise number 3. As crazy as it sounds, there are as many natural numbers as there are integers, because we are going to construct a bijection from the natural numbers to the integers. And if I have a bijective map between two sets, they are by definition of the same cardinality. So, following the hint, we try to find a number system or numbering way of numbering the integers. So here I start with number 1. 0 is my number 1. Then I go here. This is my number 2, and then I have to jump back. Of course, I can't go that way because there would be no end and I couldn't come back. So then I come here. This is my number 3. Then I jump over there. This is my number 4. Then this here is my number 5, and so on. So this would be number 6, number 8, and so on. And this here is 7, 9, and so on. And this clearly goes in both directions as long as I want to. So what happens? All these numbers get mapped to their even counterparts, so multiplying by 2. And here these negative numbers get mapped to the odd natural numbers. And this clearly is a numbering of the integers. And this is what a bijection from the natural numbers to any set does. It gives each element a natural number, and that is it. So all that is left to do is to write down explicit function term. I don't know if this is correct, the function explicitly. So we define. Okay, so what is happening? We construct a function or a map from the natural numbers to the integers as follows. For an even number, as you can see here, we simply divide by 2 and I end up with the positive integers. If my number is odd, I subtract it from 1 and then divide by 2. And then I end up with 0 or the negative integers. For example, if n is 1, this is odd. 1 minus 1 over 2 is 0. If n is 3, 1 minus 3 is minus 2, divided by 2 is minus 1, and so on. So this clearly is a map from the natural numbers to the integers. And all that is left to do is to show that this is injective and surjective, or to simply find the inverse function. Okay, now what would the inverse map going from the integers to the natural numbers look like? Well, we just have to take a look. Now the distinction is not between even and odd numbers, but between positive numbers and negative numbers. To make it even more clear that we're now going from the integers to the naturals, I call the variable now z for an integer number. And the distinction now is not between even or odd, but between positive or negative or 0. So let's look at the positive integers up here. What happens? They all get mapped to 2 times themselves. 1 goes to 2, 2 to 4, and so on. So here, for positive integers, we simply take times 2. What happens for the negative integers? We also double this one, but with a minus sign. Minus 2 times 1 is 2, and then we add 1. So we obtain the odd natural numbers here. So this is all. And for 0, I have 1 minus 2 times 0. I end up with 1. So this is exactly what happens here in both directions. And now to be completely sure that there's a bijection from n to z, we must check if this really is true. If I already called that prematurely f inverse because I know that it is the inverse, I also could have called it g, and then we have to show that the composite of g with f is the identity of n, and the composite of f with g is the identity of z. Let's do this together in one example, and you do the rest if you wish, but if you're a beginner, you should really do so. So, for example, we look at this composite here, and we plug in, for example, an odd number, so that we have this expression here. So, f inverse composed with f applied to n is by definition f inverse of f of n. Now f of n in this case is 1 minus n over 2. And now this here is our variable z that we have to plug in here. Now we have to decide, is this positive or negative? Well, this is clearly negative. This is exactly how we constructed this here, because n is greater than or equal to 1. Okay, let's do it for odd numbers greater than or equal to 3, because if n equals 1, we end up with 0 here. And then I have to use this definition, and I end up with 1, which is what I want, because if I plug in 1 here, I end up with 1. So for 1, this is the identity. Now for n greater than or equal to 3, this here is clearly negative, so we have to use this definition. So we have 1 minus 2 times so this here is our integer z, and we plug this in here for this z. Now if I multiply this, I can cancel the 2, and I'm left with 1 minus minus n, so plus n. Sorry, this was unnecessary after all, because even if this here is 0, I still apply this. So this covers all the cases where n is odd. I apologize. And now this shows that this composition here, at least for the odd numbers, is really the identity of the natural numbers, because they end up with n itself. And you can check the same for even numbers. Here it's pretty obvious that those are inverses, and also the other way around. But this is now truly left as an exercise for you. But to summarize, we have found a bijection between the natural numbers and the integers. And that means that they both have the same kind of infinity. If you say here, oh, that's not so nice, distinguishing the cases, and here I have to also distinguish the cases and check all 4 cases, isn't there a better way? Yes, there is. And it comes from thinking about what happens here geometrically or using graphs of functions. Now, if we plot the graph of this function where the variable runs through the real numbers, this is simply this line here with slope 1/2. And this here is a line with y-intersect 1/2 and slope minus 1/2. So both taken together give me this here. This together is of course not the graph of a function if my domain would be the real numbers, but my domain are the natural numbers. So then it is a graph, and it does the following. 1 gets mapped to 0 here. 2 gets mapped to 1. 3 gets mapped to -1. 4 gets mapped to 2, and so on. So I have this zigzag array of points, which is exactly what happens here. Yeah? But now this has the advantage that I can write down the functions for those 2 branches. This here is, I call this axis n, and this here z for the integers. And now here I have a map from the natural numbers to the integers. This is exactly this map here. Now this branch here has the equation z equals n over 2, and this here is z equals 1 minus n over 2. Y-intercept 1/2 and slope minus 1/2. And now, for years I taught it like that in my additional course to the math honors course, I don't know how you would say in English. And then one day, big shout out to Tom, a student of mine, very bright young fella, came up with this idea. He wrote it down a bit differently, but the idea was the same. So this here is a closed expression for all these dots here. Check it out. If we say f of n is 1 over 4 plus -1 to the n times n minus n over 2 minus 1 over 4 in parentheses, then this does exactly what both of those do. Of course, only if n runs through the natural numbers. If n is a real number, you would have to define what you mean by minus 1 to the n. Actually, if you hack this into Wolfram alpha, it gives you a nice curve using the complex logarithm and whatnot, but we restrict ourselves to the natural numbers. So if n is even, what happens? Then this here vanishes. Minus 1 raised to an even number, to the power of an even number, is 1. So I end up with 1/4 plus n over 2 minus 1/4. 1/4 cancels, and I end up with n over 2. Good. If n is odd, this here gives me minus 1. So I end up with 1/4 minus n over 2. And now minus minus gives plus 1/4. So this gives 1/2 minus 1/2 n, which is exactly this here. Now, isn't this nice? This here is, if n runs through the natural numbers, exactly what happens here. This describes this zigzag array of points in one formula. And now, what do I do geometrically to get to the inverse function? Of course, I reflect about this axis here with slope 1. This branch becomes z equals 2n. This is simply the inverse of this. And if you rotate this, this becomes z equals 1 minus 2n. Simply solve for n here and interchange. And now, because I plotted both in the same coordinate system, here I also use the variable n instead of z, because this still is the n-axis. But if you know about absolute values, now you can write this here, which clearly is a function, even if the domain are the real numbers. These two lines meet here at 1/4. If you know about absolute values, this is exactly what this function here does. So check it out. If n is greater than 1/4, because we are in the natural numbers, I can say n is greater than or equal to 1. This absolute value vanishes, because then the argument is positive, and I end up with 2n, because minus 1/2 and plus 1/2 cancels. This is exactly that. If I'm left of 1, I have to put a minus sign if I want the absolute value to vanish. So I end up with minus 2n plus 1/2, which is exactly this here, minus 2n plus 1. So this is a closed expression for the inverse function, which even works for the real numbers as a domain, but then of course also for the integers as a domain. And now I map the integers in this zigzag fashion to the natural numbers. Take a look. 0 goes to 1, checks out. 1 goes to 2, checks out. Minus 1 goes to 3, indeed, and so on. And now those here are clearly inverse functions. And if you don't believe it, you can easily check it by doing this calculation. And now the advantage here is I do not have to distinguish between even or odd numbers, or in the other way around, between positive or negative integers. So f inverse of f of n is, f inverse is this guy here, and instead of n, I plug in this whole expression here, which is simply f of n. All right? Then you multiply distributively. So here you end up with 1/2 plus minus 1 to the n. And now I pull the 2 inside of these parentheses here. Then I end up with n minus 1/2. Now this minus 1/2 and this 1/2 cancel. And I'm left with this. Now n is a natural number, so it is non-negative and greater than or equal to 1. So this here is a positive number. The absolute value is multiplicative, and the absolute value of minus 1 to the nth power, of course, is 1. So I end up with this here. And now minus 1/2 plus 1/2 cancels, and I'm left with n, which is the identity of the natural numbers applied to n, showing that this composite of f inverse and f is indeed the identity. And the other way around goes similarly, left as an exercise to you. Although this is all elementary stuff, I think it's pretty beautiful, especially in this form. Most of the time in the textbooks you find this here with the two cases distinguished, but it's also possible to write it down like that. This, of course, was a big detour from our actual goal to learn about bijective maps and has not so much to do with our subject, namely group theory, but I think it was too nice to simply leave it out.